So, gases. Up till this point, we've talked about things reacting in sort of a solid state, right, in terms of grams, or in liquids, like acids, bases, molarity kind of stuff. Now we're going to talk about gases, and before we even talk about any reactions involving gases, we have to talk about the properties of gases, because they're a little bit different than the other things, right? Liquids and solids both have definite volumes. Liquids may have indefinite shapes, but they have a definite volume, and so we define those with molarity. Gases don't have a definite volume, so that can change depending on the properties of the environment. The Maxwell equations. Well, there's a quote here. So many of the properties of matter, especially when in the gaseous form, can be deduced from the hypothesis that their minute, not minute, minute parts are in rapid motion. So the small parts of the gas are in rapid motion. The velocity increasing with the temperature. That the precise nature of this motion becomes a subject of rational curiosity. So this is actually, well, we'll get to this early on, but this is the crux of what gases are. We're going to be thinking of them in terms of what they are actually, which is small particles flying around where their speed or velocity is related to temperature. So you put pressure to work every day by breathing. This is a fun stat. You move about 8,500 liters of air in and out, which is about 11 kilograms or 25 pounds of air, if you were to take it all and weigh it. Breathing is only possible because your body is able to create pressure differences. So many things in chemistry come down to differences in pressure or concentration. So when you inhale, actually I think it's So when you're inhaling, you're actually expanding the size of the volume of your lungs, which decreases the pressure, and then air pushes in from outside. Pressure, as a formal definition, is the force exerted per unit area by gas molecules as they strike the surfaces around them. So you can define this as force over an area, and when we look at units of pressure, they incorporate both of these things. Some unit of force, some unit of area. So for gases, the pressure of a gas depends on several factors. One of them being the number of gas particles in a given volume, which you can think of as concentration, volume of the container, and the average speed of the gas particles. Now remember, these gas particles are, striking a surface. So if they hit the surface faster, they hit with more energy, increases the pressure. If there are more particles, so more collisions, also more energy. And if you have a smaller container, you can actually have more collisions because the particles are moving from one side of the container to the other more rapidly. It takes them less time to travel from one side to the other. So by inhaling, or when we inhale, we increase the volume of the lungs, which decreases the gas concentration. So there's fewer gas particles per unit of volume in your lungs. And that causes the outside air pressure to push into your lungs, filling them with fresh air. So at an atmospheric level, the pressure is super important for determining weather. So higher pressure is usually associated with clear weather, so calm weather essentially, and low pressure is usually associated with unstable weather. So currently, in the last several weeks, do you think it's a high pressure or low pressure system? Probably a low pressure system. Haven't looked it up, but probably low pressure, giving us way, way, way too much snow through that atmospheric river. The number of gas particles in a given volume also decreases with increasing altitude. So if you hop on 198, drive up to the mountains, as you're driving up, that pressure around you is decreasing because there are fewer gas particles. So the pressure exerted by a gas is dependent on the number of gas particles in a given volume. So fewer gas particles mean lower force per unit area and a lower pressure. So just comparing these two jars, and this is, well, I guess it's the same unit, but we have way more particles. There's going to be way more collisions with the sides of that container than in the low pressure container. So also feel this, right? We feel this, like I said, when we're driving up into the mountains. If you want to see some of the insane snow, you probably can't get very far, depending on how far they've cleared things out. I know China Peak's gotten over 500 inches of snow this year. It's an insane amount of snow. Yeah, very good year. And so as you're driving up there, though, there's well, when you're staying at one elevation, the air inside your inner ear and the air outside, the pressure is balanced. As you change your elevation, so if you go higher up in elevation, the pressure on the outside decreases faster than the inside can equilibrate. One of the ways you can help this along is by yawning. It opens up a little channel to equalize that pressure, but sometimes that doesn't always work. And so that pressure can build up, and it causes your eardrum to actually flex outwards because the pressure inside is higher than the pressure outside. And that can cause pain if you don't relieve that pressure. Okay, so one of the ways that we can measure pressure is with the mercury barometer. And actually, that's what this thing is. This is a mercury barometer. It was invented by, can't remember his first name, but his last name is Torricelli in like the 1800s or something. And so using this mercury barometer was happening, and actually, if I lift this up, you might be able back there to see the top of the mercury column. There's no air above this mercury. It's a perfect vacuum. And what's happening is you take this mercury tube and you fill it all the way up with mercury, and then with one end plugged, you stick it into a bath of mercury, or it doesn't really have to be a bath, but there's a pool of mercury at the bottom here. And the weight of the mercury pulls down until there's a perfect vacuum above it. Now, the height of this column of mercury depends on the atmospheric pressure outside of the barometer. So as atmospheric pressure increases, it forces the mercury farther up the tube. As it decreases, the mercury can fall farther down the tube. And so by using this, we can measure atmospheric pressure wherever the barometer is. And that's measured as the distance from the top of the pool of mercury to the top of the column. And for torr, T-O-R-R, named after Torricelli, or millimeters of mercury, it's measured in millimeters. So you can actually convert millimeters of mercury to inches of mercury to centimeters of mercury, any of those that you might like, because it is literally the distance. So it's just a distance measurement. You could do the same thing even with water, but if you did it with water, I think you need a column, well, yeah, it's 30 inches, over 30 inches tall of water, whereas this is, I don't know what this is in inches. I have to calculate it. Anyways, so higher pressure means a higher column of mercury. Getting a little sidetracked. But we do have a bunch of different pressure units. And like I said, these are units of pressure, and pressure is a force being applied to an area. So the units of Pascal is 1 Newton per meter squared. So if you took an area of a meter square, 1 meter on each side, and put 1 Newton of pressure on that, which is really, really not a lot of pressure over the whole thing, that would be 1 Pascal. And so at the average air pressure at sea level, that's 101,325 pascals. So it's 101,000 newtons on 1 square meter. Probably a more relatable unit is PSI, which is pounds per square inch. And that's 14.7 PSI at sea level. So at sea level, if you have a square that's 1 inch by 1 inch, the pressure on that due to atmospheric pressure is going to be 14.7 pounds. Or when you air up your car tires, you're actually airing up the tires to a pressure over this 14.7. So if you put 30 psi in your car tire, the total pressure would actually be 30 plus the 14.7. But we measure everything relative to the atmospheric pressure because that's sort of what it's fighting against. So 30 pounds per square inch. This is why if you ride bicycles or if you know things about bicycles, the skinny road bike tires have really, really high pressures because they have to support an entire person's body weight on a much smaller area. So they'll be up around 100, 120 psi sometimes if they're really skinny, or lower like 80, where most bike tires are wider and will be like 50 psi in that range. So we talked about the torr, and the torr is in millimeters of mercury, and so this one's a little bit different and a little weird compared to the other units because it's the height of this column rather than the force on a unit area. But we can convert it into those using these relationships. Inches of mercury is, like I was explaining earlier, taking torr or millimeters of mercury and converting that distance into inches. So pressure around here, if you're a pilot, they usually read the pilot for pilots, and over the air traffic control, they'll read it in inches of mercury. Atmospheric pressure is important for weather. Lost my train of thought. Sorry, oh yeah, if you see the weather on TV and they talk about that pressure, it'll be in inches of mercury probably. And then we also have the unit of 1 atmosphere. And 1 atmosphere is defined as the pressure at the average pressure at sea level. So 1 atmosphere is just what it is. You can take this unit of atmospheres and you can do a whole bunch of stuff and convert it and figure out what those units are. I guess to go back to Newton per meter squared, then it would be, right, this is the relationship between those two. So converting between pressure units is actually pretty simple because we've got a bunch of different units and we know what all of them are at sea level. And so to convert between them, we just use that fact. So we say, well, for example, if your local weather report announces that the barometric pressure is 30.44 inches of mercury, convert this pressure to psi. And we've got a bunch of different values here that are all equal to each other. So if you know these relationships, you can convert between any of them and make your own conversion factor between them. So since we're starting with 30.44 inches of mercury, and we want to get to psi, then if we have all of these unit conversions, we can pull this, all right, at sea level, right, average sea level, the pressure is going to be 29.92 inches, and that's equal to 14.7 psi. So our conversion factor will be built from those two. And we want to cancel out 29.92 inches of mercury. And we want units of psi, so we'll put 14.7 psi on top. So 30.44 times 14.7 divided by 29.92. And that will be, with the correct sig figs, that's funny, the answer at the top there is not in the correct sig figs. It will be 14.9, yeah, 14.96 psi. Need to look up, for now we'll assume that this is exact, because you'd think that we'd have, the textbook slides would have included more precision if there was more precision to be had. I'll double check that. But for now, assume that these conversions aren't going to affect your number of sig figs. So end up with 14.96 psi. And we could convert this from inches of mercury to pascals, or to atmospheres, or to millimeters of mercury, or to torr. Pretty easily. Same steps, you just swap out this top unit for whatever unit you want to convert it into. Okay. So, from Maxwell's quote on that very first slide, which was about kinetic molecular theory. So this is sort of the theory that underpins all of these gas laws, especially the simple gas laws, which we're going to talk about first. And I moved this from the back of these slides up to the front because I think it's important. I think this is the best way to understand gases. And so we're going to go through, and I've added in some links to the simulation, and we'll kind of try and draw our own conclusions about these gas laws. So this kinetic molecular theory is the simplest model for describing the behavior of gases. There's a sort of set of assumptions that we're making about the gas particles. And so we've got this collection of particles all inside of a container, and these particles are in constant motion. They never stop moving, they just keep bouncing off of things. The first part of kinetic molecular theory is that the size of a particle is negligibly small. So we essentially treat these as points, and they take up no space inside of the system. So this assumes that the gas particles occupy no volume, even though they do have mass. And so because they're negligibly small, they're so small that we can ignore their size, the empty space between the gas particles is huge. We'll talk about STP a little bit more later. This is standard temperature and pressure. So it's defining a set of conditions. We'll talk about those conditions later. So if you took argon, though, at standard temperature and pressure, the argon atoms would occupy only 0.01% of the gas volume. The very, very, very tiny amount of the volume. And if you were to blow one of these argon atoms up to the size of a golf ball, the next argon atom would be 4 feet away from it, the closest one. Most of them would be even farther. So tons of space. The second part of this is that the average kinetic energy of the gas particles is directly proportional to the temperature in kelvins. So the amount of speed, the amount of motion energy that each of these particles has is related to the temperature. So if we increase the temperature, then the speed or the kinetic energy of these particles increases. You decrease the temperature, and the average speed decreases. We talk about the average speed because not all the gas particles are moving at the same speed. In fact, we can describe it with the distribution. Some of them will be moving really, really slow. Some of them will be moving really, really fast. Most of them will fall somewhere in between. And we'll see that in the simulation too. And then the last point here is that the collision of one particle with another within the walls of its container is completely elastic. And all that means is there's no loss of energy when two particles collide. So if they run into each other, they bounce off, really like billiard balls do, right? If you played pool, if you shoot one pool ball into another, the one will stop, and the other ball will take off with the same amount of energy. Or if you collide two into each other, then they bounce off, maintaining all of that energy. Checking to see if anybody else is still scribbling frantically. Just let me know if we need to slow down. So elastic collision is like those balls in pool, bouncing off of each other, maintaining their velocity. If two collide at an angle, then they'll bounce off as if each of them had just hit a wall. Kind of like a super bouncy ball. So they're not inelastic collisions. In an inelastic collision, you lose kinetic energy. And it's turned into heat. All right. So try to keep these things in mind, and I'll, of course, keep bringing them up. I'll force you to keep them in mind as we go through the rest of the gas laws and try to figure out what's going to happen when we change different parameters. So the simple gas laws are the ones that were in that Maxwell quote, and this is what he was talking about. So we have 4 basic properties: pressure, volume, temperature, and amount in moles of the particles, of the gas particles. And each of these properties is interrelated so that when one changes, it affects the others. So if you increase the temperature, it's going to affect the pressure, it's going to affect the volume, it's going to affect, well, might not affect the number of moles directly. Again, we'll look at how these are exactly related. So the simple gas laws describe the relationship between individual pairs. And so when we look at these, we're going to look at two properties at a time and assume that the others, well, either assume or force the others to be constant. So if we're looking at pressure and volume, then the temperature and the amount of the gas in moles will be fixed. If we're looking at volume and temperature, then we'll fix pressure at a certain value, and we'll fix the amount of moles at a certain value. And we'll go through these one by one. These laws were originally deduced from observations in which 2 of the 4 properties were held constant, which is what we'll do in these simulations too. So the manometer, just very briefly, is one of the ways that was, or one of the instruments used to sort of measure these properties. Manometer, unlike our mercury barometer over here, is used to measure the pressure inside of a container relative to atmospheric pressure. So in this case, we have a high pressure inside of this flask. So these gas molecules are pushing down on the mercury on one side, forcing it to go up on the other side. And on that side, the atmospheric pressure is pushing against it. And so this difference in height between these 2 levels indicates the pressure of the gas relative to the outside pressure. And almost always, this is what we're talking about. We talk about, like I was saying, the pressure in your car tires. That's essentially if you use a bike pump, is essentially a manometer. You put the bike pump on, and it's telling you how much pressure is in your bike tire or your car tire over atmospheric pressure, compared to atmospheric pressure. Okay, now we're going to do the simulation. I have it already pulled up. All right, so here's our simulation. So the first thing that we're going to look at is volume versus pressure. So we'll start this. And actually, before we even do that, I'll point out, like, some of these particles, right, you can see some of them are moving really fast. Every once in a while, there's some that are moving slow. Occasionally, there will be ones like this one or that one that are almost standing still. So we're getting this distribution of velocities. So what do you think is going to happen to the pressure inside of this container? I do constant temperature. All right, so temperature is going to stay constant. Only pressure and volume are going to change. And we've got 50 particles inside the box. So if I take this box and I double the volume, what do you think is going to happen to the pressure inside the box? It's going to go down. And actually, before we do that, let's do this. So this will count the number of collisions of those particles with the walls. And it's not super, super consistent. It is a simulation after all. All right, so we got 95. Let's get a few of these. 108. Write these down. 95, 108, and the last one's 98. Okay. So if I increase this, we're going to go to roughly double. Oh, I didn't actually take, what was the pressure before? It was like 8. So our pressure over here is 8.4 atmospheres. Oh, that's right, the mouse isn't on there. 8.4 atmospheres, and so I take this and I pull it over, and it goes down to 3.9. Right, so it cuts roughly in half. And I'm just eyeballing. Oh, I just realized it's like off the screen. I'm just kind of eyeballing here what half is. See if I do. There we go. So just trying to eyeball that that's like roughly double. So yeah, our pressure drops. And if I squeeze this down again, it'll go up. But we can measure the wall collisions also. 75. And 69. And 72. All right, so the number of collisions has also decreased. Right, because the pressure inside of this container is related to how often those particles are colliding with the sides. And then so if we can put this back here, and that's back up to 8, and then we can close it down even more, and it goes up to 11.8. So our smallest volume has the highest pressure, and our largest volume has the lowest pressure. So would you say that pressure and volume are directly related, proportionally related, or inversely related? Inversely related, right? So as we increase the volume, pressure goes down. If we decrease volume, pressure goes up. And that is Boyle's law. So Boyle observed this, oh man, I said 1800s, 1600s, even longer ago. So he used this sort of J-tube manometer-like thing, and he poured mercury on one side, he had the other side plugged, and then he measured the volume of the gas on the opposite side from where he was pouring in more mercury. And he saw that that got smaller, and that it got smaller depending on how much mercury he put in, and it got smaller proportionally, or inversely proportional. So, yeah, he observed an inverse relationship between volume and pressure. And if we took this, then we could probably do it with the simulation, but it would take a long time. We could plot out this data. And we could say that as we increase the pressure of mercury, so we're pouring more and more mercury in, the volume is decreasing. And now on a graph where two things are inversely proportional, you will see this relationship if you just plot directly volume versus pressure. Right? Not a perfectly straight, it's not a straight line by any means. It's a curve. But because Boyle's law is this inverse proportionality between volume and pressure, if we plot that, pressure or volume versus 1 over pressure, we'll come back to that slide. Right? We can take this curved line and it turns into a straight line. We've got 1 over pressure as our x unit now. Which is kind of wild that a property of nature, like, you could do this experiment and it would like come out pretty close to perfectly straight. That's just how gases work. So Boyle's law, to put it sort of formally into a formula, equals P1 V1 equals P2 V2. Because the relationship between the pressure and volume of gas, as long as the temperature and as long as the number of moles remains constant, the pressure times the volume will always be constant. So that number doesn't change for a gas. As you change one, it changes the other. All right? And I'll show you a way that you don't have to memorize each of these individual laws. I also don't really care if you remember that this is Boyle's law. I want you to remember what is the relationship between volume and pressure. I don't really care about Charles Boyle. Sorry, Charles. So as the volume of a gas sample is decreased, gas molecules collide with the surrounding surfaces more frequently, resulting in greater pressure. And so we kind of saw that with the simulation, right, where more collisions equals a higher pressure. If we make that container larger, and actually, go back to that for a second. So if I make this container again really large, you can really follow any individual particle. And we could start picking a particle and then time how long it takes to get from either the left to the right or the top to the bottom. Here, the left to the right probably matters more. And it just takes longer for each particle to make a trip from one wall to another wall. So we get fewer collisions. And if we crunch this down, right, now it takes a lot less time to travel from one side to the other. There's also more stuff to run into in between. And so you end up with a lot more collisions. Do one collision counter. Yeah, so 123, that's higher than what we had before. So the reason that this happens is because of these collisions. That's why kinetic molecular theory is important, because it explains why this happens. And if you know why it happens, you have to do less memorization work. This is also, Boyle's law is super important when diving, because once you go underwater, you're not only being pressurized by the air above you, which, think about this for a second, at sea level, if the atmospheric pressure is 14.7 pounds per square inch, that is the mass, the weight, the force of the entire column of air above you all the way to space. So that's what you're feeling in that 14.7 pounds per square inch. When you go underwater, water is a lot more dense than air, hence why it doesn't float in the air. And so if you go even 1 meter underwater, you're going to feel a lot more pressure than a 1 meter change in elevation, right? Which we don't notice at all. But you go down 1 meter underwater, and your ears will probably pop or start to hurt. It's about, well, I guess we know 1 meter is about 3 feet. Yeah, it's not that deep. If you go 3 meters down, sorry. Okay, but for every 10 meters, so you go 3 meters down, that's like a 9-foot pool, right? More than that, probably more like 10 feet. Yeah, you probably start to feel that?
Yeah, you feel it, yeah. Our pool at the deep is like 13 feet.
Uh-huh.
And you can really,
yeah, 13 feet. Yeah. So now imagine if you go down 10 meters, so 3 times that, and you're doubling atmospheric pressure. So you're adding another additional atmosphere of pressure on your eardrums. And if you go down 20 meters, you'll experience approximately 3 atmospheres of pressure, because now it's not just the air above you, but it's also all of that water. And so if you're diving and you hold your breath and then rise to the surface, when you're down at, well, I guess this just says a diver holds his breath and rises quickly to the surface. Doesn't say how deep. But let's say you go down 4 meters. Right? You're down there at 4 meters, you've got roughly 2 atmosphere and almost a half of pressure on your lungs. That breath at that depth, as you rise, is going to start expanding in your lungs because the pressure around you is decreasing. And so you can actually cause damage to your internal organs by that rapidly increasing pressure, or rapidly increasing volume. Expanding at a factor of 3. You always want to exhale while you're rising. Most of us probably aren't diving that deep, ever. That's pretty far down. We can do some interesting calculations with this, though, just using Boyle's law. So if we take a syringe, so if we have a snorkeler, and they take a syringe filled with 16 milliliters of air from the surface, where the pressure is 1 atmosphere, 1.0 atmospheres, and they take that down to an unknown depth. The volume of the air in the syringe at that new depth is 7.5 milliliters. What is the pressure at this depth? If this pressure increases by 1 atmosphere for every 10 meters of depth, how deep is the snorkeler? So we're going to use Boyle's law. P1 V1 equals P2 V2. And if we look at sort of the information that we're given here, it's kind of a lot of information, but we want to break this apart into 2 different sets of conditions. So we have our snorkeler at the surface, and we have the snorkeler at some unknown depth. So what is our P1 and our V1 going to be? Yeah, P1's 1 atmosphere, we should do 1.0. And V1, yeah, 60 milliliters. And then our P2 is what we're looking for in atmospheres. And our V2 is going to be 7.5 milliliters. Now the nice thing about the simple gas laws is that aside from temperature, and we'll talk about temperature, the units don't really matter but the units that go in are the units that come out. So in this case, if we put in, or I should say, the units matter in as much as whatever you put in has to match what's going to come out. So if we put in units of 1 atmosphere, then our pressure that comes out is going to be atmospheres. If we put in milliliters, then as V1, then V2 also needs to be in milliliters. So this is going to be 1.0 atmospheres times 16 milliliters equals P2 times 7.5 milliliters. So 1 atmosphere times 16 milliliters will give us 16 atmosphere milliliters. And we'll divide that by 7.5 milliliters. And then milliliters will cancel. So that's 2.1, well, it's 2.13 repeating. So 2.1 atmospheres equals the pressure. Now, how do we figure out how deep the snorkeler dove? Yep, it gives us the unit conversion from meters of depth to atmospheres. So for every we'll get 1 atmosphere of additional pressure for every 10 meters of depth. So is this, but the atmosphere at the surface is already 1 atmosphere. So the diver's pressure only increased by an additional 1.1 atmospheres because it's the extra pressure over what it was at the surface. So we have to take our 2.1 atmospheres and subtract out the 1.0 atmospheres from the surface because you got an additional pressure of 1.1 atmospheres. And then we can take our 1.1 atmospheres times 10 meters over 1 atmosphere, so that our pressure is, our depth is 11 meters. Yeah.
So if we were to do it in a problem like this, that's the final depth, final initial times that conversion factor.
Mm-hmm.
That would work for any different pressure. So even if you start at surface, started like 10 meters deep, another 10 meters, it would still work.
Yeah. Yeah. So if he started from 10 meters deep already and his pressure, or let's say he starts at 11 meters, right, and it's 2.1, if he dives an additional 10 meters below that, then the pressure increase would be, I guess it would go up to 3.1 atmospheres, right? But yeah, so for any, it's really the difference in pressure. So you could do it, for one depth to another depth, from the surface and down. Yeah. I think the trickiest thing about gas law problems is just figuring out which simple gas law to use, especially if there's distractor information involved. Here, there isn't any distracting information, so if you knew that the temperature is constant and the number of moles is constant because it's in this sealed syringe, then pressure and volume are the only things that are changing. And those are also the units that we're given. Okay, so let's look at another relationship. So now we're going to look at when we have constant pressure. I should also write here that this is also going to be constant moles. So go back to this one. Let's make this a little bit bigger. And then I want dependent variable as volume. Okay. Now for this, our temperature units have to be in Kelvin. The reason is Kelvin is an absolute scale of temperature. And it's directly related to the motions of particles. Because does anybody know what 0 Kelvin means? Absolute zero is what? Yeah. Yeah.
You said it first.
Absolute zero means that the atoms and molecules of the material have completely stopped moving. There's no more kinetic energy in that atom, molecule, whatever it is. So we haven't reached absolute zero yet. And even space, right? Because space is like as cold as it gets. It's not. I think it's like 2.7 Kelvin. So it's very, very, very cold, but it's not absolute zero. And so because of that, we have to use Kelvin scale for this, because we're talking about the relationship between the kinetic energy of these molecules or particles, and in this case, the volume. So what's going to happen? What happens if I increase the temperature? The pressure will go up, but we've got constant pressure on right now. The pressure is going to stay constant. Number of moles stays constant. I'm increasing the temperature. Yeah, we get more collisions with the walls, which will increase the size of the walls because then we want the pressure to stay the same. So adding energy, the box expands. So we go up to like 500 Kelvin, and then I can also cool this down. I know, right? It makes ice, right? So increasing temperature increases volume. Decreasing temperature decreases volume. So what is the relationship between volume and temperature? Directly proportional, right? So increasing one increases the other. And it's because it's trying to keep the number and the energy involved in the collisions the same. Let's see here. Okay. So this is Charles' law. It's the relationship between volume and temperature when we have constant pressure and constant number of moles. And so the way you describe this mathematically is that volume divided by temperature equals a constant. So if the volume divided by temperature equals a constant for any gas, then at constant pressure, constant number of moles, we could say if it goes from one set of conditions of volume and temperature to a new set of conditions of volume and temperature, we can predict what the new volume is going to be if we know the temperature, or what the new temperature is going to be if we know the volume. And this is like the one absolute is that we always have to be in Kelvin. Celsius and Fahrenheit are both relative scales. So you know that 32 degrees Fahrenheit is 0 degrees Celsius. What is 0 degrees Fahrenheit minus 0 degrees Celsius? Because we know that 0 Fahrenheit is 32, or sorry, so this is like saying 0 degrees Fahrenheit minus 32 degrees Fahrenheit. But 1 equals 0, 1 equals negative 32. It's because they're both relative scales. And they're both, for both of them, 0 was just somewhat arbitrarily set at a certain point. So this is really a meaningless thing because we're setting sort of the origin point of both of these scales and we're trying to subtract them, and it's nonsense. But it looks really silly. You may see people on the internet claiming that math is a lie because of this, or science is a lie. Okay, so V1 over T1 equals V2 over T2. You can also take this, volume doesn't have to be on top. You could put temperature on top. If it makes it easier to solve, you can rewrite this as T1 over V1 equals T2 over V2. The thing that you do have to keep consistent is that if temperature is on top for one, temperature has to be on top for the other. Okay. So you can actually calculate, using Charles' law, calculate absolute zero in degrees Celsius. So because the temperature of our atoms is related to the volume, so if we decrease the temperature all the way, at some point we're going to reach zero volume. And that zero volume point is where the atoms of the gas have completely stopped moving. So if you start from reasonable temperatures and you start to do this sort of experiment, you cool down a gas, you measure the volume, you cool down the gas, you measure the volume, keep going, at some point, right, it'll condense, it'll become a liquid. But if you take the gas portion of that line, which will make a straight line because they're directly proportional, you can draw a straight line through it all the way to negative 273.15 Kelvin. So you can do this with different numbers of moles, and they'll all point to exactly the same spot, which is absolute zero. Because we can't have negative volume. All right. So again, kind of looking at this molecular view and really talking about kinetic molecular theory here. If we take this balloon and we move it from ice water into boiling water, the balloon will expand in the boiling water because the gas particles are moving faster, which means that they're colliding with the sides of the balloon harder, which stretches the balloon out because it's always going to maintain a constant pressure. So if you ever get a question involving a balloon, pressure is going to be constant because the pressure inside a balloon is always equal to the pressure outside the balloon. When we start lab, I'll go and look and see if we have a soda bottle and a balloon. So if you put a balloon into a soda bottle and blow it up, and then you can squeeze the soda bottle if you put a cap on it, and the balloon inside the soda bottle shrinks. As you increase the pressure inside the soda bottle, it increases the pressure on the balloon, and so it shrinks to match. I'll see if I can't find that stuff. But this has to do with the kinetic energy inside of the balloon versus the kinetic energy outside the balloon. So temperature does two things actually for increasing the volume. The first is that you get more collisions. I guess the first one we talked about was that the force exerted by each collision is greater because as you increase the temperature, you increase the average velocity of all of your particles. They're moving faster, which means that they hit the walls harder, and they hit the walls more frequently because it takes them less time to travel from one side to the other. And so we can reduce the amount of force on the sides of the walls to keep it constant by increasing the distance from one wall to the other. So if it takes more time to get there, then there's fewer collisions. This is how hot air balloons work. And in hot air balloons, you're decreasing the density of the gas because it's occupying more space. And then this is a balloon thrown into liquid nitrogen. So it would be a regular size, balloon at room temperature, throw it into liquid nitrogen, and it shrivels way up. All right, but to do the math with this, so again, we've got V1 over T1 equals V2 over T2. Gas in a cylinder with a movable piston has an initial volume of 88.2 milliliters. If we heat the gas from 35 degrees C to 155 degrees C, what is its final volume in milliliters? So I'll draw a picture because this comes up a lot. The sort of piston here with a movable slider, kind of like the simulation. So this is the piston that goes up and down. All right, so if we've got a gas in here, we've got 88.2 milliliters inside right now, and we're increasing the temperature. What should happen to the piston? All right, it goes up, and that means that we're going to increase the volume. So we should see a higher volume. So our volume, V1, is going to be 88.2 milliliters. T1, 35 degrees C. V2 is what we want to find. And then because similar to the other simple gas, well, just like the other simple gas laws, if we put in volume units of milliliters, we'll get out volume units of milliliters. The units that we use for volume don't really matter because those are absolute units. But what do we have to do before we can actually plug any numbers in? Temperature to Kelvin. So to go from Celsius to Kelvin, we add 273.15. Uh, 35 plus 273.15 is 308.15, and then 155 plus 273.15 is going to be 428.15. All right. So now we can take these and we can plug them in. So if we get 88.2 milliliters over 308.15 Kelvin equals V2 over 428.15 Kelvin. A little algebra magic. Oops. 88.2 divided by 308.15 times 428.15. So our new volume be 123 milliliters equals B2. Yeah. Need to go through and correct the sig figs on these. It should probably be 35.0.
They are.
No, well, the temperature's not. But if 35 has fewer decimal places, when we add them together, we should have, well, since it has no decimal places, we'll have no decimal places. Although, even with 0 decimal places, we end up with 308, which is still 3 sig figs. So I think it does end up being 3 sig figs. Because this is 2 sig figs, and this is 5, right? But because it's the number of decimal places, we keep 0 of the decimal places. So these 3 would be significant. And then because we're doing multiplication after that, we can keep that. I haven't figured out a good way to articulate why addition and subtraction works like that, and you can kind of get more sig figs. But it comes down to, it's really hard to measure small things. It's easy to measure large things. And so you're limited by how closely your divisions are here. But if I add up, if this had, well, I guess we're using a graduated cylinder and it's 50 milliliters and 50 milliliters, I can be very sure that there's 50 milliliters, 50.0 milliliters in both of those. When I add those together, I'll also be very sure that it's 100 milliliters. And the uncertainty is still in that 0.1 milliliter place. So you can kind of gain sig figs. Weird as it is. All right. All right, so if we have the pressure exerted on a sample of a fixed amount of gas is doubled, so pressure exerted is doubled at constant temperature, and then the temperature of the gas in kelvins is doubled at constant pressure, what is the final volume of the gas? So what happens when we double the pressure? Yeah, so if we 2x the pressure, that'll be 1/2 the volume. But then if we double the temperature, yeah, so if we 2x the temperature, or 2 times the temperature, right? Then that'll double the volume. So the overall effect would be, yep, the final volume of the gas is the same as the initial volume.
It was weird for me to think not the other way. I
Mm.
would think having double the pressure. Weird to think of that as a cause and effect.
Yeah, think of it like if you take something deep underwater, right? You double the pressure that way, take it 10 meters underwater, and then you've doubled the pressure, and so it's going to crush it down to half the volume. But yeah, I know what you mean. All right, back to the simulation. So we're going to talk about volume versus moles of a gas now. And for this one, actually, I think I keep it on this one. Pressure? No. Pressure, constant volume. Yeah, so I'm not going to change the temperature, but the volume will change as I add more gas. I guess I just gave it away, right? So if I add more gas particles in here, what's going to happen to the volume? Why does it increase?
There's going to be more collision.
Yeah, there's going to be more collisions. So if I double it, what should happen to the volume? Twice as many particles, twice as many collisions. Boink. They just injected a whole bunch more particles in there. And actually, you break the simulation like this, it'll tell you that it can't do anymore. Well, let's go ahead and do that. Right? Oh, too much.
Too hard.
Oh, it did. It's reset this. Yeah. So I can take out half of these particles. Now, one of the interesting things is so we're treating all of these particles that are inside of here the same. So I added light particles. We got light particles in there right now. What happens if I add heavy particles? So if I add in 50 heavy particles, is it going to more than double the volume? Because they're heavier? Ooh, will they be moving at the same speed? I don't know what the simulation is going to make it do. Let's assume, because, okay, so temperature, right, is going to be the average. We're keeping temperature here constant. So if the temperature stays constant, let's just see what happens. All right. I'm doubling the number of moles of total gas, but I've got 2 different types of gas.
What is the molar mass? Oh.
So it still doubles. So the volume doesn't care, but the heavy gas particles, because they're so much heavier, they move slower. But the temperature is not directly just the speed, it's the kinetic energy, right? So if I, at 240 pounds, ran and charged somebody and tackled them, right, that amount of energy, wait, actually, where was I going with the analogy? Okay, my 14-year-old little brother, he weighs 140 pounds, right? He'd have to run twice as fast, roughly, to get the same amount of energy that I would. So I'd have to move slower because I'm large and heavy. He has to move around faster, but has the same amount of energy. So for gas particles, this is essentially the same thing. If temperature stays constant, heavy particles are just going to move slower. They'll collide with the walls with the same amount of energy, though. And so their effect on the volume here, we're looking at moles versus volume, is going to be the same. Won't change anything. Okay. So go back. This is not Avocado's law. I was trying to think of some avocado toast joke there to make, but I couldn't. So Avogadro's law, the relationship between volume and amount of moles. This one actually I think is almost the most intuitive. Why does the balloon get larger when you blow it up? You're adding more moles of gas to the balloon. So yeah, this was first stated by Amadeo Avogadro, that the volume is proportional to the number of gas molecules. So if we increase the number of gas molecules, then we also, increase the number of gas molecules, then it'll also increase the volume when temperature and pressure are both constant. So that's the key. Temperature and pressure are both constant here. So we can count the number of gas molecules by moles and then use that in this equation. Equal volumes of gases contain equal number of molecules. The identity of the gas doesn't matter. So that's why if we had the heavy particles versus the light particles, it doesn't change. The physics don't change. So because this is a directly proportional relationship, we can plot number of moles versus volume, and we get a straight line. Right? For every doubling of the volume, we also double, or for every doubling of the number of moles, we also double the volume. So extrapolation predicts that 0 moles of gas would occupy 0 volume. Right? So if you take this all the way back, right, take all the moles of gas out, it's going to occupy 0 volume. Makes sense. All right, so which action would cause the volume of a gas sample to increase? Decreasing the pressure, decreasing the temperature, or decreasing the number of moles? Yep. Decreasing the pressure. So if we decrease the pressure on a cylinder, so if I draw another cylinder, I'll just do it like this. If we decrease the pressure, so there's a pressure on the outside pushing down that's fighting against the pressure on the inside pushing up. And so if the outside pressure goes down, and these get smaller, then the inside pressure will start to win that, and it'll push the cylinder up. And decreasing the pressure is the only one that's inversely proportional to volume. Right? Everything else we've talked about has been directly proportional. Increasing temperature increases volume. Increasing moles increases volume. Okay. So if we have a chemical reaction occurring in a cylinder equipped with another movable piston, the cylinder with a movable piston is going to become all too familiar. Our chemical reaction produces 0.621 moles of gas if the cylinder contained 0.12 moles of gas before the reaction and had an initial volume of 2.18 liters. What was its volume after the reaction? Assume constant pressure and temperature, and that the initial amount of gas completely reacts. And essentially all of this at the end here is to say, just use the numbers that are in the question as they are. Okay, so our cylinder, well, we're going to be using Avogadro's law, so V1 over N1 equals V2 over N2. And this one, just like Charles' law, which was temperature and volume, we can flip both sides of this, so we get N1 over V1 equals N2 over V2. So what is V1? Yeah, an initial volume. That's your key, 2.18 liters. And what's N1? 0.120 moles. So V2 is what we're looking for, right? It says what was its volume after the reaction. So after the reaction, V2 is going to be question mark. What will what will volume 2's units be? Liters. And then N2 is our 0.621 moles. So unlike that earlier diver problem, we don't need the difference in moles. We just need to know what the amount of moles is. So 2.18 liters over 0.120 moles equals V2 over 0.621 moles. So we're going to multiply that 0.621 moles to both sides. This will be 11.3 liters equals V2. And that makes sense too, because we added more gas. We created more gas inside of this piston. The volume should increase to keep pressure and temperature the same. Kind of run out of time here. What was this next one? All right, I'm going to skip that one because we've got to do the ideal gas law. We could, well, here, I'll show you how to set this one up. So we have this blimp that's filled with helium to a volume. Well, it'll rise if it's filled to a volume of 55.0. What is the lowercase d? Decimeters cubed. So a decimeter is 1/10 of a meter. This is 1/10 of a meter cubed. And we can see, we're told that when 1.1 moles of helium is added to the blimp, the volume is 26.2 decimeters cubed. How many more grams of helium? I don't want to use red. How many more grams of helium must be added to make it rise? So the key here is to first figure out how many moles of helium you need, and then use the molar mass to calculate how many grams. We got to move on. So I want to talk about the ideal gas law before we close out lecture today. So ideal gas law takes all of the previous sort of simple gas laws that we've looked at, all of those relationships, and boils them down into a single equation. No. Boils them down? That was good. Thank you. Unintentional pun. Boils them down. Okay, so we get the single equation. Now, the thing that's really special about this is that this works for any ideal gas under any conditions, and we don't need an initial set of conditions. So with the simple gas laws, you have to know either the initial set of conditions or the final set of conditions. So for Charles' law, for example, because that's one off the top of my head, you have to know the volume and the temperature at one point in time. And then you can calculate it for any other temperature or any other volume. The ideal gas law, though, will let you calculate the volume as long as you know the pressure, the number of moles, and temperature. R here is this special relationship, which is constant for all ideal gases. So when we looked at like Charles' law, Boyle's law, Avogadro's law, volume divided by temperature equals a constant. Pressure times volume equals a constant. Avogadro's law is volume divided by number of moles equals a constant for a gas. And for all gases, we can take all of those constants and get R. And R's units are very, very important, and you should always remember them and always write them down because they tell you the units that you need in the ideal gas law. So liters, atmospheres per mole, Kelvin. Yeah. Yeah. Right. Yep. Use 8206, because I think also last semester, did we use 273.15 or 273? 0.15? Yeah. So actually the R, here, we'll do this. This will be the last thing. R is calculated from the set of conditions where, well, from a standard set of, well, it could, sorry. We can calculate it at STP. So STP is standard temperature and pressure, which we're probably going to get here in just a little bit. But the standard temperature is 273.15 Kelvin, and the standard pressure is 1 atmosphere. And we can calculate that for 1 mole of gas, and that's how you get R. Oh, and sorry, 1 liter. Oh, no, sorry. The volume, 22.4 liters. So the volume of 1 mole of ideal gas at STP is 22.4 liters. So depending on if you plug in 273.15 versus 273, so I'm going to plug all these in to calculate R equals pressure volume over NT. So the pressure is 1, the volume, so 1 atmosphere times 222.4 liters over 1 mole times 273.15. So if you do 22.4 divided by 273.15, that gives you you need to use more decimals for, you have to use more decimals than just 22.4 for the molar volume. So it's like 22.41 something, so that 22.4, and that'll give you 273, or sorry, that'll give you 0.08206. 22.4 divided by just 273 is closer to that 0.0821. We're going to use this one though, because it incorporates more precision in the numbers that are used to calculate it. Oh, actually, one last thing. So if R is always equal to PV over NT for any gas, this is where we can take this and use it to find all of the simpler gas laws, and that's why the conditions where those things are constant are important. So the conditions of a gas under one set of conditions, PV over NT, and we call that P1V1 over N1T1, is equal to P2V2 over N2T2. So under any new set of conditions, those things will change in such a way that they always equal R. So when we make things constant, so we say constant N and constant T, what that means is those values aren't changing. So if N and T don't change going from N1 to N2, T1 to T2, we can leave them out of the equation. Bring this over here. So we can leave those out of the equation, so if we erase them, then we get P1V1 over P2, or equals P2V2, which is Boyle's law. If we make N and P constant, right? Holy cow, you chill? So P1 over N1, P2 over N2, those things become constant. Now it's just V1 over T1 equals V2 over T2, which is Charles' law. And if we keep pressure and temperature constant, let's take in the V1 N1, T1. All right, so if pressure and temperature are constant, and we erase those, then that gives us Avogadro's law. So they all kind of fall out of this when we make things constant and you remove them from the equation, they become the simpler gas laws. All right.